So today I want to say just a little bit more about stereochemistry. I don't think we'll need to spend a huge amount of time there. And then we're going to talk kinetics. So you'll hear terms thrown around from time to time, and you should be aware of them and know how to use them correctly. Stereospecific is the one that is perhaps used most incorrectly. A lot of people say stereospecific when they mean stereoselective. A stereospecific reaction is a reaction where a particular stereoisomer of the starting material, I'm going to just use the abbreviation there, a starting material stereoisomer gives a particular product stereoisomer. And if you switch stereoisomers in the starting material, you get a different product stereoisomer. And I'll show you some examples of this, but usually this occurs because of specific mechanistic details or implications. For example, one of the key mechanistic implications is that if two different diastereomers go through the same reaction and give different diastereomer products, there can be no common intermediate between those two diastereomers. They can't ever, midway through their reaction, intersect with the same molecule. Otherwise, it wouldn't work out that way. Sometimes it means the reaction's concerted. Other times it means the reaction has particular stereochemical requirements. But the classic examples of stereospecific reactions include epoxidation. So you're used to the idea that if you, start with the transalkene, you're going to get the trans epoxide. If you start out with the cis olefin, you're going to get the cis epoxide. Notice that you can tell the reaction is stereospecific because you have diastereomers here that each lead to different product diastereomers. Okay? And the reason that works is because the reaction is concerted. The oxygen gets added to the olefin from one face of the olefin, so stereochemistry is preserved. Another classic example of that is the SN2 reaction. I'm just going to write down these examples that are given in a table in your book because they're less boring than the examples I might think of, so kind of fun. Adding thiophenolate to this particular tosylate will give you the axial thioether, whereas if you instead started with the axial tosylate and did the same reaction, you would get the other diastereomer. Okay, and why is that? Well, we know in SN2 generally proceeds with inversion of stereochemistry, inversion of stereochemical configuration at the location of the leaving group, in part because the nucleophile has to attack the sigma star where the leaving group is. And there are some other examples. E2 is a stereospecific example. One of my favorite test questions in 351 was to give people some alkyl bromide with chiral alkyl bromide with specific stereochemical relationships between the groups and say, okay, do the okay, hey, that's fun. Do the elimination reaction, and you should only get one product. And what is it? Well, it's for this. It's the one where the phenyl groups are cis to each other. And of course, if you used a different diastereomer, you could get the one where the phenyl groups are trans to each other. And if you don't believe me, go look at the book and see if you can figure that out on your own. I don't know that we need to belabor the point. There's one example in your book that was troubling to me a little bit because it demonstrates that reactions I sound way too fancy for an American there. Needn't be 100% stereospecific. So they just have to have an inversion, or they just have to have a switch in the major product when you switch stereoisomers in the starting material. So Grignard addition to ketones that have stereocenters on the alpha carbon, ketones or aldehydes with stereocenters on the alpha carbon, can be an interesting example of this. And I think we'll probably talk about the origin of this stereospecificity or stereoselectivity. But there is a preference for the conformation where I don't want to make stuff up, so I'll just show you the results. Starting with the enantiomer of the aldehyde enantiomer shown, you get the majority of your product from the methyl Grignard attacking the aldehyde from above, and then you get a smaller but still measurable amount of the diastereomer where the methyl Grignard attacks from below. And the interesting thing is, if you switch the enantiomers switch stereochemical configuration, the product ratio, you still have a 2-to-1 ratio of products, it's just in the opposite direction. So instead here, when the methyl group is up on the alpha carbon, you have a preference for methyl Grignard to add from below. That's now 67%, and I guess we'll move that here. Whereas the smaller stereoisomer is the one where methyl Grignard adds from above. So what you see here, the reason this is called stereospecific is because when you switch stereoisomers, you get a flip in the ratio, okay? Now, you would also call this reaction diastereoselective because there's one diastereomer that is preferred over the other. Okay? On the top, this is the diastereomer that's preferred. On the bottom, this is the diastereomer that's preferred. Am I getting that right? Did I screw anything up? I think we got it. However, you can call it stereospecific because when you switch products, when you switch starting materials from one enantiomer to the other, you switch what the major product is. Do you see actually how these two major products are actually enantiomers of each other? All right. So again, it's diastereoselective, and reactions can be diastereoselective even if the starting material doesn't have stereoisomers available to it. Diastereoselective is a term that you can apply to a single reaction. The reaction on top is diastereoselective for the major diastereomer, okay, where the methyl groups, one is up and the other is down. The reason it's stereospecific is when you switch to the other stereoisomer of the starting material, you get a different stereoisomer as the major product. Okay, and you can say, oh, well, this reaction is only 67% stereospecific because you still get some of the product where the methyl Grignard adds from the other side. Okay, so any questions about what stereospecific means? Okay, stereospecific observations are crucially important because they tell us a lot about mechanism, and we'll talk about those kinds of things again and again and again. Stereoselective just means one stereoisomer is preferred over the other, whether or not there are stereoisomers possible in the starting material. As an example, and we're not going to worry about how to rationalize this. It turns out there is a way to rationalize it based on things you learned in Chapter 2. But the lithium aluminum hydride reduction of this ketone, there's no stereoisomers possible for the starting ketone, but there are stereoisomers possible in the products. You can either have a trans orientation between the T-butyl group and the OH group, or they can be cis. The observed product ratio sort of tracks with what you might expect for stability of products, though I'm not sure that's the reason here. Lithium aluminum hydride reduction is irreversible, and when a reaction is irreversible, the relative stability of the products doesn't matter. What matters is which product is fastest to form. So what you'd have to do to rationalize this is explain why it's better for lithium aluminum hydride to add to that ketone from the top face versus the bottom face. And it probably has to do with proximity of axial protons on the alpha carbons, whereas from the bottom face you've got to deal with these guys, and from the top face the axial protons are a little bit further away. Okay, so that's an example of stereoselective. Another example where stereoisomer is possible is the E2 reaction, where there's lots of different protons beta to the leaving group, and therefore you're going to get a mixture of cis and trans olefins and the monosubstituted olefin, and experimentally that's at about a 60-20-20 ratio. Yeah. And it turns out if you tried the other enantiomer of that bromide, you get the exact same ratio of products. The stereochemistry in the starting material doesn't turn out to matter here or influence the Diastereo selectivity among the products. Now, if you run a reaction that favors one enantiomer over another, you can call that enantioselective. And those kinds of reactions are particularly useful if you can use some kind of chiral reagent to induce a major stereoisomer, a major enantiomer as a product. All right, any questions about stereoselective versus stereospecific? I'm sorry. I think I was deceptive a little bit. Diastereoselectivity refers to the fact that you get a preference for trans over cis. How about the preference for the more substituted alkene versus the less substituted? What's that an issue of? There's a word I'm looking for. Sure.
Those are constitutional isomers.
They're constitutional isomers, so what do we put in front of selectivity to describe. What's that? Regio. Yep, regioselectivity refers to selectivity of one constitutional or regioisomer over another. Constitutional isomer is a mouthful, so often organic chemists will use regioisomers. It's a slightly restricted version of constitutional isomer. It has mostly the same connectivity except for some key feature. So we call these olefins, the mono versus disubstituted olefins, regioisomers, and regioselectivity is preference for one regioisomer over another. A lot of the trends you learned in sophomore organic were related to regioselectivity, right? E2 favors the more substituted alkene. What else? Addition to alkenes, you're going to get electrophilic addition to alkenes. The proton goes on the less substituted carbon so that the other thing that comes in can go on the more substituted carbon, Markovnikov versus anti-Markovnikov, and so on. All right, so those are terms you should be used to, be ready to sort of throw around and understand, particularly in talks that people give, especially the methodology organic chemists, the ones that are trying to invent new reactions. They're going to show you lots and lots of tables, and they will try to impress you with the various levels of stereoselectivity of their reactions. And so you got to know what they're talking about. If the reaction's stereospecific, then stereoselectivity is not that impressive, right? Ooh, you started with one enantiomer of your starting material and you got one enantiomer of your product. Good job. Everybody can do that, right? That's the SN2 reaction. All right. So I want to talk now, if it's okay, about kinetics. And we're going to start, so this is chapter 7. I have posted study guides for chapters 5 and 6. I don't know if I put due dates on them yet. I also realize that we need to schedule an exam. I'm not in any particular hurry to do that, but we probably ought to do it before it gets too close to the end of the semester. Again, I will offer you the chance to give me feedback. If you absolutely hate the oral exam format and wish it were something else, we can consider that. I haven't yet decided what we're going to do. Scheduling, I'm clearly not going to do it this week. If there's a particular time next week that's better, you can let me know that as well. I'm very flexible. The further away it is, the longer I have before I have to write it, and the longer you have before you have to take it, and that's sort of mutually beneficial at this point. Let's contact me with any questions or concerns, and by Friday we'll schedule a date for when the next exam's going to be, and I will tell you what the format's going to be. I think probably it would be most useful, this exam will include chapters 2, 3, 5, and 6. So I don't know that there's any need to put kinetics on it. We can put that one to the next one if that's all right. You're like, sweet, now I don't have to listen to the rest of this lecture. Yes, good luck. That is a good strategy. All right. So we're going to talk about the concept of a potential energy surface. And this is a better concept. This is a great concept that's very difficult to illustrate effectively. I love that Jack shows up there just with his fake stubble. Yes, oh my gosh. I forgot about that. Jack, buddy, I love you. You look good with or without facial hair. So this is a potential energy surface. And you can think of the y-axis as representing energy. Duh. In particular, it's most effective to think of this as free energy, which governs whether reactions are spontaneous or not. For the most part, because entropy doesn't often in many reactions doesn't change a lot, and because enthalpy is directly correlated to bond strength and interaction strength, a lot of people will think about enthalpy as being on this axis. But another way to think of it is just overall molecular potential energy. And whether you think that in terms of Gibbs free energy versus enthalpy is fine. Now, a lot of times people will show you potential energy surfaces and they won't tell you what the axes mean, and that is deliberate. Because this is one arbitrary degree of freedom, and this is another orthogonal arbitrary degree of freedom. And because humans are terrible at visualizing objects that are more than three-dimensional, we sort of stop there. But you have to realize that these potential energy surfaces are actually multi-dimensional hypersurfaces. That's kind of cool. Sounds like hyperspace. And they have 3n minus 6, I guess, horizontal dimensions. That's not correct, I'm sure, mathematically, but what I mean is instead of having only 2 degrees of freedom and then the potential energy axis, we should have 3n minus 6 axes that are orthogonal to the potential energy, and n here equals the overall degrees of freedom, and n is huge for larger molecules. This includes translation of the whole molecule in X, Y, and Z. It includes tumbling, some kind of arbitrary, whoa, we're flipping around, tumbling in space. I'm not sure how many degrees of freedom there are. Pitch, yaw, and roll, maybe. So maybe there's 3 more tumbling degrees of freedom. Then within the molecule, there are bond stretches. There are bond rotations. There are bond angle distortions. And more. Okay. So this represents, basically the potential energy surface represents how the energy of the molecule changes with all of the possible ways its geometry can change. Peaks here don't represent, mountain peaks here don't represent transition states. Peaks actually represent really high energy structures or geometries that are rarely, if ever, populated. Okay, the valleys represent low energy geometries or structures. Let's see. So this could be intermediates, starting materials, products. And one thing you got to think of is that each valley is spanned by quantized vibrational levels. Maybe you remember from PChem having a one-dimensional potential energy surface of like hydrogen, H2, and how there are various quantized energy surfaces as you for vibration of various quantized energy states, vibrational states, and there's no way actually to get to the very bottom of the well because even at the lowest vibrational state, you're still not at the bottom. So you can think of these sort of horizontal levels within each valley that molecules can populate. Go ahead.
the peaks also have horizontal quantized levels?
Do the peaks have horizontal quantized levels? I think if you get above the peaks, usually you get to the point, the higher you go up in energy, and even here, the closer you get to breaking the bond, the more close in energy the vibrational levels get until they're mostly continuous. Yeah. Oh no, the evil recording bar. Thank you. I'm sorry. Yeah. Valleys are characterized by minima. They are minima, of course, in the potential energy surface. So if we were to take the first derivative of the energy surface with respect to one of the degrees of freedom, let's just call it x, like the x-axis, that first derivative should be what at the minimum? 0. Okay, that makes sense mathematically. Turns out that has a physical meaning that I didn't appreciate before I started to read this chapter. And it's not that important, but I kind of geeked out on it, and since I'm the instructor, I can share all the things that I geek out about. So if you remember in physics, when you calculated how much work it would take to move an object from point A to point B, what you did for work is take the force you applied to that object and multiply it by the distance that you travel the object through. Now that, of course, assumes a frictionless and spherical cow, and then also a constant force applied through a distance, right? Whatever. Well, work is actually, we learned, the same thing as energy. And if you want to get a little bit more technical, you can say, okay, the energy expended in a process is the integral of force over distance from 0 to x. Alternatively, you could say that dE dx equals force. Force is the first derivative of energy with respect to some distance coordinate. Okay? Force is first derivative of energy. And so what that tells you is that at the minimum in this valley, we've identified that minimum as being a place where dE dx equals 0. The force on the structure of the molecule through all its degrees of freedom has to go to 0. Does that make sense? Say it again.
What exactly do you mean by force on structure?
Well, okay, so what we mean by forces acting on the structure. Think of a molecule having a particular geometry sort of rolling around the bottom of this energy well, right? As it goes up the energy surface, there is a force because its energy is higher than it can be. There's a force pushing it down back into the energy well. Just as if I go up to the 4th floor, my potential energy is higher and there is a gravitational force pulling me downward. Yeah? So, I mean, we're sort of starting with the mathematical definition on a potential energy surface of the valley being a minimum, and therefore first derivative of energy with respect to some coordinate has to equal 0. Yeah?
So the force is 0 at the bottom. How do you ever get out of it?
So the forces are 0, but remember that's describing potential energy, and we haven't accounted for kinetic energy yet, right? So what gets you out of the valley is the average kinetic energy of the molecules, right? Similarly, so think about riding your bike. Suppose you're at the top of one hill, suppose you're at one of these saddle points, which we haven't talked about yet, and you roll down here, you had potential energy here, you're exchanging it for kinetic energy here. And if that kinetic energy is sufficient, you can convert it back into potential energy to surmount the next hill. And we'll see that the average kinetic energy of molecules is just another way of saying temperature, right? Temperature is just the average kinetic energy of molecules. I think I told you about my nephew who's on the autism spectrum and sees the world in really unique ways, telling his mother when it was cold out one day, wow, there's not a lot of jiggling going on out there of molecules. So, right. So we'll call points at which the first derivative of energy with respect to some distance or degree of freedom coordinate, we're going to call points that satisfy that stationary points. And of course, minima in these values, remember, we're not only talking about 2 degrees of freedom, we're talking about 3n, we're talking about n degrees of freedom with 3n minus 6 horizontal dimensions. So this would need to be a stationary point, or a true energy minimum would need to be someplace where all of the dE dx values equal 0. All right? Oh, but wait, there's more. What do you know about first derivatives? They equal 0 when? When you're minimum or when you're maximum, right? Oh, well, now that's kind of a problem, because what that means is there are multiple places where dE dx equals 0. We're going to mark them in blue for stationary points. Sure, here at the bottom is a place where dE dx equals 0, but actually there is one, because that's a maximum along one dimension. And then this is also a place where dE dx equals 0. So we got 3 sort of bad, we got 3 places. And if we want to, or if we're interested in locating and calculating energy of minima and transition states, we want to know where stationary points 1 and 2 are, but we don't care about point 3 because it's rarely populated. Okay? So what is the trick in calculus for telling whether your spot where first derivative equals 0 is a minimum or a maximum? Let's just look at the difference between this versus this. Okay, at both of these points, we'll say this is E and this is X. At both of these points, dE dx equals 0. What's different though? Go ahead. The concavity. Okay, so one second derivative. Right. Second derivative you can think of as concavity, you can think of it as gradient. Remember, first derivative is instantaneous slope. At that point, the slope is 0. But second derivative should be, how is that slope changing? Okay? So for the picture on the right, where this is a minimum, what is the sign of the second derivative? Should it be positive or negative? Is it increasing or decreasing? It's positive, right? Slopes used to be negative. They go to 0, now they become positive. So overall, that the first derivative of the first derivative is positive. Or I suppose we could say greater than 0. Okay? So true minima will be places where all of the second derivatives of energy with respect to some degree of freedom coordinate will be positive. Okay. So in contrast, for a maximum, the slope here was positive, it went to 0, and then it became negative. So that means that at a maximum, d, the second derivative of energy with respect to some distance or some degree of freedom coordinate will be less than 0. Okay, so that's how we tell minima from maxima. But how do you tell a saddle point? Okay, a saddle point is sort of the lowest, it's the mountain pass. It's the lowest space to get over the mountains without doing anything extra that you have to do. How could we distinguish a saddle point from, say, the top of a peak? And let's just assume this two-dimension, this is just a, let's assume we know everything about this surface. We only have 2 degrees of freedom. What distinguishes the saddle point from the peak? Go ahead.
It's a minimum in some coordinates and maximum in others.
Okay, a saddle point is a maximum in one and only one direction, and a minimum in all the others. Okay, so look at, we're going to zoom in on this saddle point. And for the sake of our discussion, we'll say this is X and this is Y. All right? And I'm going to draw the trajectory of a molecule from this valley through the saddle point to the valley represented by blue point 1. So point 2 is a max along the X coordinate. But if you look at the Y coordinate, which we'll represent with this green line, it's actually at a minimum. The curve slopes up from that point. Okay? The saddle point is going to represent our transition state for a reaction. And you can tell a saddle point because at a saddle point you will have let's see, you will have second derivatives of energy with respect to distance greater than 0 in all directions but 1. Or you will have second derivative less than 0 for 1 and only 1 degree of freedom or distance coordinate. Okay? So in a lot of ways, that's just extra math to describe this potential energy surface, but it actually is pretty important. One of the ways it's used a lot in optimizing structures and calculations. Michael, you do some of this, right?
Oh, yeah.
So when you're looking for a minimum, you're looking for, what will the log file tell you?
The log file would give me energy that it without an imaginary number in it.
Okay.
I assume that's where you're going.
Yeah, well, what the program has done is it's evaluated the second derivative of energy with respect to X, Y, and Z for each atom in the structure. And that second derivative needs to be positive in all possible directions, meaning anywhere you move an atom, it's higher in energy, right? How about a transition state? If you want to identify, and this is a thing I didn't know, like how do you identify a transition state, which is a maximum? And the trick is you tell the computer, look for a structure that has positive second derivatives with respect to X, Y, and Z for everything but 1. And that will tell you that you're at a maximum, at the minimalist maximum in your potential energy surface, right? Because we're not interested in the maximum at the top of the peak, because nobody ever goes there unless you're insane. That's not true. Humans like to climb mountains and we like to get over the peak. But molecules are going to traverse, on average, the lowest energy pathway from one valley to another. And the way you find that is you find something that's a maximum in only one coordinate and a minimum in all the others. Okay? Yeah.
And does such a point always exist? Because if that paths were up higher, presumably it could be a maximum in multiple.
Sure. Does that point always exist? Certainly not. And that's why there are molecules that are very not reactive, I guess. I mean, or they may or may not be accessible. Yeah. Go ahead.
If the only way to get from A to B is going over a peak.
I'm not sure about that. So I'm sure there are weird shaped potential energy surfaces that we haven't considered. Yeah.
What if there are multiple transition states and they're different energy?
Multiple transition states. You mean a multi-step reaction?
Sure.
Okay.
Yeah.
That would be, so if you look at this potential energy surface, imagine going from, and these minima slash saddle points are actually called stationary points on the potential energy surface, because for all of them, the force on the particles is 0. But yeah, if you're going from this one, if you're going from this valley over the hill to this one, yeah, you've got two different transition states.
Okay. And so when we're talking about it being maxima in only one direction, but minimum in all the other ones, and the other transition state is taller than the first one, maybe I'm just not understanding how.
Okay, well, you're doing the calculation at this point, right? So at this point, the first derivatives are all 0, and the second derivatives are all positive except for 1. And that tells you that if you move along that coordinate, you can move down in energy. Same thing at this point. Now, what distinguishes one point from the other? Well, they're far apart in geometry and they're different in energy. So yeah, we're not, all of this is about examining sort of the local properties of the surface. And it's a different question as to how you explore a global minimum in your calculations. And one way you can do that is have lots of different starting points. Yeah. I just want to illustrate the saddle point a little bit differently by showing you an image from the text that gives you a sense for what a saddle point looks like. Sorry, moving stuff out of the way. Oh, I don't like horizontal vertical distortion in figures. It drives me crazy. Right, so here we're starting out in one valley. I'm using blue for stationary points, I guess. Here we're starting out in one valley, and we're crossing into another. And you can see that the minimum energy pathway is sort of traced out for you in orange. Okay? And here, from this perspective, it's easier to see that at the saddle point, if you move in the other direction, we're only considering two coordinates, as if this molecule only had two possible ways to change its geometry. If you move in the other direction, it's uphill. But if you move along the same direction, it's now downhill. And that is because at that transition state, the second derivative of energy with respect to the distance or whatever coordinate is negative at 1 and only 1 coordinate. The sort of cross section of the potential energy surface along this saddle is called the COL, which I'm not sure how to pronounce. Coal. I don't know whether we should pronounce that as though we're in the Midwest or whether we're in Boston. So coal, maybe. Michael, do you know? Is this even a thing, or are they just making this stuff up?
I don't know.
Okay.
I've never heard of it.
Okay, I haven't heard of it either. Go ahead.
I think that term is not used for describing actual mountains and pathways for climbing.
Oh, okay. So maybe it's from mountaineering. That's cool. Another interesting point is that molecules don't all traverse the same way over the saddle point. They have so many different degrees of freedom and so much kinetic energy that one of them may approach the surface in a more winding way, others may go here, and what you're observing when you actually measure a reaction rate is sort of the weighted average of all the paths taken over that saddle point. And one important theoretical point that chemist Henry Eyring realized was that along this call, whatever it's called, that there's a regular distribution of how many particles are here versus here versus here versus here versus here instantaneously, and there's a relationship between their location on this surface and the overall energy. In other words, if you call this the transition state, along the coordinate, the further away you get, the less particles there are. And that kind of assumption is going to be interesting because Henry Eyring's transition state theory makes the assumption that, did we run out of, nope, I don't know what happened here. Oh, that's dumb. I don't know why virtual experience thought it was that important. Anyway, that's right. Lab party, okay. You really in this COVID climate want to stick your face in some VR thing that a teenager has disinfected? Yeah. Randomly, yeah. My children would, not likely. Anyway, we'll come back to this because the idea that the more commonly traversed pathway is the one that's lower in energy, but there's sort of a distribution of pathways taken, will be useful in transition state theory, where you actually pretend that there's something of an equilibrium operating between the transition state and the valley. All right, so we'll more later. Again, please email me if you have questions or concerns about the exam format, if you have a preference to when it would be good next week. I'm thinking Thursday, but if you'd prefer it to be like never, you can tell me that also, and I will laugh at you.
I think we all feel that way.
That's right. All right, so with that, have a great Wednesday.